Thanks very much. Okay, so I'll be talking to you about the Atacama Large Aperture Submillimeter Telescope design study. So it's a telescope that doesn't yet exist. And my slides won't change. There you go. So I think I have to go very quickly in trying to convince you of the need of such a telescope. So first of all, as you know, about half of the light in the universe is emitted in the far infrared and submillimeter. And you can see here in the lower, yes, here in this part of the slide, how the center of our own galaxy gets brighter and brighter as we move from the optical towards the submillimeter. You can also see here at the top right, the different kinds of physics and information we get when we observe in the optical and in the submillimeter, and same goes for the bottom right, where submillimeter observations help us resolve things that until recently we thought were just one single blob into protoclusters at very high redshifts. So at the same time, even though interferometers can offer huge knowledge nowadays, they are very powerful follow-up machines, but they are limited by usually small field of views. Of course, high resolution, but still very small field of views, at best a few arc minute wide. And in fact, most of the sources that nowadays interferometers like ALMA and NOEMA are following have been discovered initially by single dish observations. So soon enough, ALMA is going to find itself in a sort of a source starving regime if another new telescope with bigger capabilities, stronger capabilities doesn't come along. And of course, single dishes are also crucial for the development and testing of new instrumentation that eventually ends up on the interferometers. There is also another aspect of this. As you know, all interferometers suffer from the so-called missing flux. So they resolve out all the fluxes that correspond to scales larger than the minimum baseline, and the minimum baseline is by default larger than the telescope diameter. And this can become a very big issue in many science cases like ISM, CGM, or IGM studies. Here I show you two examples. At the bottom left, you can see a simulation of a nearby galaxy, and you can see the input and what in fact you observe with ALMA, because you are missing all this large scale emission. And to the right you can see a filament in the Orion. So in the middle you have the ALMA 12 meter only, and to the left you have the IRAM 30 meters. And in fact, if you don't combine the two, you will be missing more than 90% of the flux in this filament. So indeed, large single dish observations are essential if you want to understand the physics of what it is that you're observing. So why we need a new and a larger one? Well, because first of all, most of the existing single dishes nowadays are small. They have small apertures, small collecting areas. This means low spatial resolution, and they can only get, of course, the most extreme of sources. There are a few large aperture facilities, such as the 50 meter, the LMT, the IRAM 30 meter, or the Nobeyama, which is 45 meter, but none of them can observe at frequencies above 400 gigahertz, either due to design and surface accuracy or due to their location. And there is a scientific pressure to deliver observations at higher frequencies if we want, especially to sample closer to the peak of the dust emission. And this is where AtLAST enters the game. AtLAST is a design study. It's funded by the European Commission Horizon 2020. We sent in a proposal under the call Development and Long-Term Sustainability of New, well, you can read it, there's a mouthful, under a specific topic, design studies. And it's part of the Research and Innovation Action Program. It's been funded for 3 years. We started in March 2021, and we already requested an extension of 6 months due to the pandemic situation that was granted. And the biggest delivery of this design study will be a construction-ready design for an AtLAST-like telescope. We have 6 work packages. The first one is led by Claudia Ciccone at the University of Oslo. This is that of the general management. The telescope design, site selection, and telescope operations work packages are all 3 led by ESO people. Telescope design by Tony Roszkowski, the site selection by Carlos de Broek and the telescope operations by myself. The work package 5 is that of the environmental sustainability and is again led by the University of Oslo by Sabrina Santori. And finally, the maturing, work package 6, the maturing of the science cases is led by Pamela Klassen in Edinburgh. Now I want to stress here that this is not an ESO project in any way. The three of us just happen to have what is needed for this project, and this is why we are leading these individual packages, but we're doing this on our science time and not on our ESO duty time. We also have an external advisory committee led by consisting of experts both in science and technology. And as I mentioned, we started off in March 2021. Now, AtLAST is driven, so the design is driven by unique science requirements. And what we want is not to do incremental science, but we want to do transformational science. So here I try to summarize a bit the minimum and the goal specifications. So I'm not going to go through all of them, but I want to stress that we are aiming at a minimum of 40 meters, ideally 50-meter telescope of a field of view of minimum 1, preferably 2 degrees. Let me see, what else can I say? The site altitude will definitely have to be above 4,800 meters and much better if it is above 5,000, but we'll come back to that later on. And we hope to reach wavelengths up to or down to 350 micron or frequencies out to 850 gigahertz. So there is, as I said, there are concrete science cases that are driving the telescope design. So I will go very briefly through them. One is studies of the galactic plane of the Milky Way. So we want to perform the deepest, highest resolution and most complete survey of molecular gas clouds, dust, protostars, and protoplanetary disk in our own galaxy and in the local group. We want to detect and image the cold material stored within the halos that is not visible via other means, and to provide a complete view of the baryon cycle in and out of galaxies. We also want to conduct submillimeter SDSS-like extragalactic surveys. And the idea is we could cover, in fact, the SDSS footprint within a couple of years. And finally, resolve, especially the Zunyaev-Zeldovich effect, both the kinematic and the thermal components. Yeah, basically, these are the 4 driving forces behind the design. So a bit more in detail, I will really go very quickly in the interest of time here, but we are aiming at a variety of surveys, from pencil beam surveys to, as I mentioned, SDSS-like submillimeter surveys, and also mapping the molecular gas in our galaxy. And when it comes to the distant universe, we are hoping to survey the high redshift star-forming galaxies, mapping of galaxy clusters out to very high redshift, trace the dust composition across the universe, and the effect of the supermassive black holes in the galaxy evolution. Now I'm going to go through, I'm going to give you some details for each of the work packages involved. As I mentioned, the first one is led by Claudia Ciccone, and this is that of the general management. The telescope design is led by Tony Roszkowski at ESO, along with Matthias Reichert from MT Mechatronics, which is now called OHB Digital Connect. This is our industrial partner, and they have very, very many years, more than 60 years of experience in building some of the largest telescopes that are currently in operation. And here I show you some of them, so from the 100-meter telescope in Effelsberg in Germany to the 25 European ALMA antennas, to the telescope, the 40-meter telescope in Yevez, to an optical telescope design, the GMT, to mid-dishes concept for the SKA, etc., etc. And this is, in fact, one of the largest work packages of this work that aims at delivering a construction-ready design roughly 2 years into the project. Very quickly, this is an on-axis hybrid Nasmyth Cassegrain telescope. You can see the mechanical mounting on the left, and you can see the optical design to the right. Just to mention that also the instrumentation is strongly driven by the science cases we want to cover, and several types of instruments are looked into. In terms of detectors, well, we often get the question of how we're going to populate the foreground plane. In fact, time is on our side in this because the number of detectors is increasing by a factor of 10 every 7 years. So by the time AtLAST is on sky, we're hoping to be in the megapixel regime, and if it goes well, after 30 years of its nominal operations, we will have reached 10 gigapixel. Regarding the site selection, so this is led by Carlos de Broek, as I mentioned. We are looking at a high place around the Chajnantor plateau, where the transmission is better than most places in the world. In fact, the only place where it's better is at the peak of the Chajnantor, where CCAT will be, but this is above 5,500 meters, and this poses a number of issues. First of all, the telescope is not going to have a dome, which means that wind is going to be an issue. So we are trying to find a place where it's not very windy, or at least where we very well know where the wind comes from and how to place the telescope with respect to it. Accessibility is an issue because we want to make as much use of existing infrastructure. And also the Chilean labor law is very strict when it comes to operating above 5,500 meters. And for all these reasons, it looks like we're going to be closer to the Chajnantor plateau rather than the peak. The work package 4 is the operations plan. This means observations, so science operations and technical operations, which I lead. In fact, we're looking into a variety of operating models, on-site versus remote, versus visitor versus service mode. We're looking into data flow systems. We're looking into maintenance scheduling, operational budget, links to the sites for the transportation of people and data. And of course, in fact, the pandemic taught us very many lessons in terms of, crisis management and the importance of accessibility, remote accessibility, and various other things. So it has been a very educational period this time, while we observe how the facilities worldwide are responding to these needs. We're also looking at adapting existing infrastructure, namely base camps and roads. We would like to use as much as possible what is already there in terms of roads, in terms of power, in terms of internet base camps, etc. So all these fall into this work package. And we are planning or hoping that this is going to be the first facility that will be fully green, fully powered by renewable energy. This work package is led by Sabrina Santori at the University of Oslo. The department there has a huge experience on renewable energies. Now remember that this is a radio submillimeter telescope, which means that it will have to operate day and night. So the requirements of the energy are quite high, but we're still hoping that
this is your 2-minute warning.
Yes, thank you very much. We're hoping that this is possible due to the number of sunny days up there. And in fact, the idea is, so we are going also to invest into storing this energy, because this is still problematic, and eventually also providing energy to the local communities from the excess energy that we may produce. Well, the design study has several outcomes, but as I said, the most important is that we will deliver a construction-ready design, including operation planned for the telescope, or an AtLAST-like telescope. After that, a lot of work will have to continue on the instrumentation, and also a lot of work will have to be done to convince funding agencies, to find partners, to team up with other efforts, for example, the Japanese LST, and to finalize a site agreement with CONICIT. And I would like to finish by saying that it's the AtLAST design study is an open collaboration. Please contact us. I know you cannot click on the link. I'm going to put it in the chat. If you want to contribute with your knowledge and expertise in any of the work packages, please feel free to fill it. It's a very small form. You just need to say which work package you want to contribute to, and we'll get in touch with you. So, and with that, thank you very much.
Thank you very much, Avanthia. Thank you for keeping the time. Any questions? Avanthia, can I ask you a question on the budget? So you have this European program that is funding you. How do you see the project developing in terms of funding? Because obviously, at some point that has to become an ISO project, or?
Well, the funding is for the design, right? So we got 3 million euros for the design only. As I said, this is not an ISO project, and ISO doesn't have any obligation to actually take this on board. It can be, you know, international collaboration. It can be whatever it is. Also, an AtLAST-like telescope was in the roadmap of ALMA, in the sense that the complementarity to ALMA is essential, but it was also made clear there that this is quite outside the scope of ALMA. So for the time being, nobody wants to claim ownership or even venture saying that, you know, maybe we'll see. So this will be difficult. However, there is a huge need and push from the community. So hopefully, you know, somebody will decide to put their hands in their pockets and and fund it.
Right, right, yeah. I mean, who are the big players in this? So ISO obviously is one, but I mean, how about US or Japan? Is there?
Well, as I said, I mean, ISO is not, that's the whole point. And this is not about constructing the telescope. This is about conducting a design study, okay? So there is, I mean, this is not a project to build a telescope. This is a project to deliver a design that is ready to be taken by whoever wants to build this telescope and do it. So beyond,
I understand that, but who's the big player that actually can do that? And ISO is one of them, right? But obviously they cannot commit yet, but who others could potentially, which others funding agencies could potentially, you know,
well, in principle, all big agencies that are currently funding astronomy worldwide could contribute to that. I mean, this is most likely going to be a collaboration, an ALMA type of thing. It's not going to be the endeavor of a single entity or a single funding agency. So I think many there are possibilities.
Okay.
Major funding agencies to contribute.